Anyway, Johannes is going to tell us about his work working with Patrick and with Amii.
And with
You're
Amii.
working a lot with Amii, right?
I do, yeah.
Yeah.
And that last author.
And yeah, Klaus.
Klaus from you.
That guy.
Okay.
Yeah. Because everyone knows him. Well, that might actually be true for all the senior people.
Take it away, Johannes.
Okay. Okay, thanks. As Rich kindly said, I'm a postdoc with Patrick, and that basically means I like to apply things to other things. And I brought you a talk with a really long title, but the main idea is I'm going to talk about neural networks, I'm going to talk about control engineering, and how we might bring the two together. And I want to start with a question. Process control, do I even care? And some of the people here might be like, yeah, but wait, maybe we do. And here's why. So this is an example for control engineering or for process control, like making sure this rocket actually launches upwards and not sidewards or, God forbid, even downwards. That's process control. In this particular case, it's done right. Unfortunately, we also have examples what happens if process control is done wrong. And I think we all heard about this one. So what do I want to say? I think it's important. I think we should care, and especially if we want to not only think about algorithms, but also what we can do with our algorithms, we should care even more. Okay, I'm going to try to keep the engineering part as short and as easy as possible, but there's a few things I have to talk about, and this is the typical control closed loop setup. So we have a plant, and that might be our airplane, that might be our rocket, and we have some way of measuring what it does, lifting up, straight up. This is our system output. And then we mostly know what we want our rocket to do, which is in fact going upwards and not sideways. And we can compare the two, and we get an error. And this error can then be fed into a controller, which does some control action, and ideally the error is 0 during running. So this is the most common control setup, and it's also called a feedback loop for the apparent reason of having a feedback. It is, and it's important to notice, it is strongly dependent on the controller model, right? There's very basic controllers that are linear. There is nonlinear control. There's a lot of people who are way better than control theory than I studied this and did a lot of work on this. So there's an abundance of approaches. What I want to talk about is one particular controller, and it's called a PID controller. So what we have is the same setup. Now we're having a look into the control box, and we have, I'm too short, way up here, we have a constant that we multiply with the error. So that basically the intuition is if I'm far away from where I want to be, I need a strong force that drives me back. We have one constant that deals with the integral of the error, so how far have I been off in the past? And we have one constant that deals with the derivative, basically meaning how's my error evolving? Is it getting better? Then I might have a smaller constant. Is it getting worse? I might have a strong constant on that part. And then we get the control action U, which is basically just summing all of them up. And this is actually, like, it's very easy, it's very simple. It's unfortunately also prone to changing conditions and disturbances, but it is still the most widely used controller. It is estimated that about 80% of industrial control is done with PID controllers. So very limited, but everywhere. So as it's a linear controller, it is mostly applicable for linear systems. And if the system is not linear, then we linearize it and really, really hope that we're not leaving this linearized area. Oh, by the way, if you have any questions, just feel free.
Are those constants?
Yes, thank you. That is a very important question, actually, for this talk. They're constants. What usually happens is someone, a control engineer, a lab assistant, adjusts them based on the response that you get, and then they are never touched again.
They do by
They do it by hand. Well, there's like software, like you can automate it, but it's basically like, this is my system, this is my impulse response. So you give like an impulse and you observe the response and then you tune your parameters and they're never touched again. And this is actually exactly what I think we should not do.
Wait,
Yeah.
Question on two.
Sorry.
When you compute the integral over all the errors at the time, are you just keeping a running sum or how?
Yeah.
Okay.
It's usually what's done. And
So
the,
it's not an exponential moving average? Or it could be, I guess?
could be. Yeah, and coming back to your question, Ross, exactly that's what I'm suggesting. We should not take constants, but we should adjust them as we go. So the idea is bringing machine learning into the setup by basically taking what we already have, which is the observations about our system and the knowledge of where we want our system to be, and feeding this into our neural network, for example, and then have our neural network spitting out appropriate, hopefully, parameters for our controllers.
So the network is spitting out those gains,
Yeah.
and those are themselves like waves.
Mm-hmm.
You could have adapted them. Instead, you're adapting the parameters of the network that are producing the gains.
Yeah. I'm not saying this is the only way to do it. It's one way to think of it. And the reason I thought of it exactly this way is it keeps the structure of the PID controller intact, right? And it outsources all the machine learning part into this black box that, because control engineers are really, really difficult when it comes to, you should try something new. They're really grumpy about black boxes. They're really grumpy about neural networks.
As long as they can't see it.
Yeah, well. So that's why I decided that this would be one way to go that we want to investigate.
Of course, to do that, you need to be able to backpropagate through the control system.
I would, yeah.
Gradients.
And I circumvent that by doing it numerically. So I adjust the weight, and then I see how the result is, and then I know whether it's better or worse. So it's kind of an iterative numerical process. It's not classical backpropagation. Yes?
You're going to tell us more.
Huh?
Tell us more.
I'm actually not going to address that further because I want to talk more about the general idea and about something a little bit different, but I'm happy to talk about how exactly we train it. But I don't think that's in my opinion, that's not the most important part or not the part that I want to talk about today. What kind of neural networks did I use? I used very simple 3-layered neural networks, just because I decided to. We have the inputs, the error, and the system measurements. We have 9 neurons, and the number is basically mainly determined by 2 input neurons because I have 2 measurements, and by 3 output neurons because I have 3 PID parameters. And then I allow arbitrary connections. So it's not feed-forward. It has arbitrary delays, arbitrary connections. And in the first approach, we just tried simply 10 random ways. In the second approach, we actually tried to evolve them try to test different connections using a genetic algorithm. And that, not surprisingly, it worked pretty well. We found good candidates. Rich is looking a little bit alienated again.
Are 1 and 2 of those are scalars? Every circle there's a scalar. Vectors also.
That's just, so these scalars are just the number of the neuron,
I know that.
and this is the feedback. G to the power of -1 means it's delayed by 1.
So I'm going to add that to the.
So the output of this neuron is fed back into this neuron with a delay of 1,
So I
as an example.
and then add that. Okay,
So we have recurrence happening because control engineering is a process that is very sensitive to time, and it doesn't make just intuitively, it doesn't make sense to use a feed-forward network if you have a problem that is such dependent on time. Basic idea like LSTMs, why do they work better? Okay, and I actually implemented 4 systems, but I'm going to talk about 2 today because I don't have that much time. And these systems represent the most common challenges that we face in control engineering. So one is the inverted pendulum. And the task is basically, what I can do is I can apply a force to this card. And the task is to keep the pendulum upwards in its unstable equilibrium. And what it basically means is an equilibrium is a point where the system is stable. If the equilibrium itself is stable, that means if I push it, it's going back to where it was. And if it's unstable and I push it, it doesn't. So control task is keep the pendulum up and keep the card within a certain range. And here we have a chaotic system. Why? Because chaos is very challenging for control engineers. It's considered one of the most challenging tasks. And just very briefly, what we have is we have this ring, and there's a fluid in it. That's why it's called fluid system. And we have a heater, and we have cooling water flowing on the outside. And what we want to do is by adjusting the heat, we want to get a constant flow in this loop. And I'm later going to show what happens if we don't have control actually. But first, I want to talk about the pendulum, because it's a little bit more intuitive, I guess. So this is what happens if we apply the standard PID controller, an LQ regulator, which is one of the standard model-based approaches that you would choose for such a system, and our approach in the black dashed line. So what you can see is they're all doing a fairly good job initially stabilizing the pendulum to 0. Like this is the card position, this is the angle. And they're all doing a good job, and then at t equals 10, we basically kick the system pretty hard. And the way we identified how hard we want to kick it is we did iterative experiments and kicked it a little bit harder every time until only one controller was able to retrieve it. And of course, that was not included in the training data. I don't think I have to say it, but it's safer to do so. And here you can see the controller output for all three algorithms. And basically what it means is it goes to 0, so the adaptive or neural PID controller actually has stabilized it because we don't need a control action anymore. And and here you can see like 2 out of 3 algorithms as the disturbance is defined fail. Yeah.
So the lowest graph is the force that the controllers are applying, right?
Yeah.
And so they're different initially. Does that mean the initial conditions are different, or they just handle them?
No, they just handle it differently.
So
they're all initialized to the same value, which is the card being at a certain position and the angle being a little bit bigger than 0, because otherwise it's trivial. Yeah. And as those graphs are kind of not as intuitive, I programmed a little demo for you. And we're going to see the PID controller, the LQR regulator, and the approach that we're suggesting. So as you can see, it's initialized close to equilibrium, which is a standard approach. And then at some point, we will kick it. Yeah, and everything goes to hell. This is the second, the model-based approach that is considered standard. And again, does a pretty good job in the beginning. Doesn't handle the disturbance as well. And this is the neural PID controller. It's a little bit more shaky in the beginning, but as you will see once it's kicked, does a pretty good job, or it actually is able to retrieve it at all compared to the other ones. Okay, back to the presentation. So that's the first that looked pretty, oh yeah.
Did you have to adjust how frequent the 3 parameters get updated?
That was given by the actuators for all the, so
It's the same.
it's the same, yeah. No, they all have the exact same conditions, same starting conditions, same access time. What we do is we allow the system to adjust the control every 10 milliseconds, and then the control action is kept constant for 10 milliseconds, and then the next choice is made.
Did you look at the actual change of the parameters?
I did. It's not in because I felt I would lose too much time. But I'm having another example, and there we can talk and see the PID parameters as they are adjusted. Yeah.
How is the training done? Like, was it trained? Is it initialized from scratch, or was there some training of the neural?
There was training in advance, yeah. So what we do is similar to what you usually do in control engineering. Is we created an impulse response, and then trained on that, and like training set, test set, validation set. But again, the disturbances were not included. Okay, so this is actually, I really like it, but I'm biased because I'm an engineer. This is the chaotic fluid system, and this is what happens if you don't control it. Like we have, this is the difference between the velocity at A and B. So we want it to be 0. Yes, Rich.
What are we seeing in the picture?
That's the system again.
Is it
Oh, that's a tube. Yeah, like it's a
cross-section of a tube?
yeah,
or
yeah.
tube?
Sorry, the engineer again. That's a cross section of a tube. Like it's a ring, and there's water in it, right?
Is it a cross-section of a pipe, or is it the pipe itself?
It's a cross section of the pipe. Like if you had the pipe like this, that's a cross.
The pipe is going around.
The pipe is going this is the pipe, and we're cross cutting this way.
So is the third dimension, is it a tube, is it a donut?
Yeah.
Donut, as opposed to a torus.
Oh, sorry, that was the question. Yeah, it's a donut.
So you're trying to get fluid to move around the loop?
So the fluid is in here, right? And we want to have the fluid have a constant flow based on the heating power and based on the cooling water. And it sounds... because it's a well-investigated chaotic system.
And how would you get it to move?
You get it to move by the difference in temperature between the heater and the cooling jacket.
What are the control issues? You get to control how hot,
Yeah, you get to control the heater.
and also there's the fluid, or is that constant?
No,
So there's 1 degree of freedom.
yes.
How hot?
Yeah, 1 degree of just the heater.
So it's constant.
Yeah.
There's a symmetry you need to break.
Sorry. I'm not getting...
Clockwise, counterclockwise.
Well, that's the thing. If you don't do anything, this is what happens. It goes counterclockwise first, and then it reverts itself and goes clockwise. I didn't make that up. That's how it works. That's thermodynamics. Actually, it's fluid dynamics.
Initially move here, right?
Huh?
It's not, it has like an initial...
So we start here, and then we have... Huh? I don't have a movie on that. Sorry, I ran out of time of making demos. Sorry. So
I just don't see any reason why heating or cooling would make it.
So I don't know how much time I have to explain that, but because that's like a whole semester of fluid dynamics. I'm not sure we want to stay that long.
I know this pendulum, I want the pendulum to not fall down.
Yeah.
What do I want to have happen here?
So for example, you could very easily think of this as being a fluid circle in a power plant, right? You have.
What I want, the graph I want.
Oh, the graph that you want is you want this to be 0 all the time.
0, okay?
Yeah.
I like 0.
That easy.
You want the flow to be 0?
No. What this is the difference between A and B. The difference in flow velocity. Like if the flow at A is exactly the same as the flow at B, then this is 0.
So imagine you had a cooling system, right? You wanted to push water through in a plant. That's what it's modeled
Yeah,
after.
exactly.
So if you have a power plant and you need water flowing through for cooling,
You don't want the water to reverse and the hot water getting back into the core.
you want a steady flow.
Wow, this is causing more distraction than I thought. Okay, let's go on then. Okay, so again, we use the standard PID as a baseline because that's what we're extending, and we're using something called backstepping, which is an algorithm that is guaranteed to be stable. Like it's something called Lyapunov stability, and people who are smarter than I have proven that it is stable. Interestingly enough, again, in the beginning, everything's fine. All three algorithms do a good job. But at the time t equals 5, what we do is we change the cooling water temperature without telling the control algorithms, of course. And as we only have a limited access to the system, again, like this 0.1 millisecond where we can adjust the input, the backstepping and the standard PID actually break. And what you can see, like you can see how that happens here, they're basically ramping up the power of the heater all the way up, and then all the way down, and then all the way up, and all the way down, and that actually results in this movement where the flow is constantly switching its direction, which is not what we want. And then I forget who asked about the PID parameter. This is how they adapted over time, and I want to outline something that I found really interesting. If you look at, so the dashed line again is our approach, and this is basically exactly the same. The further our system is away from where it's supposed to be, the higher this constant Kp, which is proportional to the error, gets. So that is like a sanity check. This is exactly what we would expect and want to happen. And sorry, I don't have a demo for that. What I do have is I have numerical results, which is exactly as exciting. So everything's done over 50 independent runs to ensure statistical evidence, and the p-values are below 0.01. No, sorry, 0.05. To one approach being considered better, what we can see is for the inverted pendulum, this is the means, this is the variance for all approaches. We're doing as good as or even better than our competitors. Oh, sorry, I forgot. We have 4 experiments for each system. We have with and without disturbance and noise. So we have 4 systems, 2 systems. We have without noise, with and without disturbance, making 8 comparisons. Yeah, I guess the numbers are then self-explanatory. We are definitely better if we have a disturbance with the pendulum, because the other ones tipped over. And we're significantly better if we have disturbances for the fluid system, because the other ones didn't converge anymore. We're only better by a small margin if the process is ideal, which is what you would expect as the standard controllers are adjusted or designed for the ideal thing without noise. Okay, and now I have to stress you a little bit again, because I initially said if we want to do control engineering, we're going to have a hard time convincing any control engineer. If we just say, look, it does better, like that's nice, but there's no guarantees that anything really works if things get messy. So what we did is we thought about what do control engineers do, in fact. And what they do is they prove stability. It's that easy. And just a very, very intuitive way, this is basically the output based on the P here is what I can adjust with the control parameters. So the P are the poles in my transfer function. You don't really have to know where that comes from. But the important thing is, if this P is below 0, then everything's going to blow up, because it's exponential, right? So all I have to do is I have to look how my PID parameters are adjusted by the neural network, and then I can compute these poles. There's tons of functions implemented in MATLAB, Python, whatever you want to do. And then I can actually check whether what my neural network does is stable or not. And for control engineers, that's really exciting. So just to give you an idea, these are the poles. This is the complex plane. And if my pole is over here, then my system is stable. If my poles are here, then it wiggles around a little bit, but it still gets stable. And if my poles are positive, everything blows up. So it's a very easy way to check whether whatever my neural network suggests actually makes sense from a control engineering point of view. So that's what we did. And this is, again, the chaotic fluid system. And The shaded areas are unstable areas. Note that the system still becomes stable, evidently. There is no guarantee, though. It's the same with convergence. Something that doesn't have a guarantee to converge still can converge. And here, these are the poles. Here's the 0, and you can see everywhere where there's one pole that is above 0, things become unstable. So this is like, there's two things that I want you to take away from the slide. The first one is, once the system has settled, it is in fact stable, so that's good. That's a good argument. I'm almost done. And the second thing is, now that we have a means to evaluate the output of our neural network in terms of what we wanted to do, we could incorporate that in our training. We could say, I'm going to penalize you based on whether you output stable parameters or not. And that's really cool, because we have now, in this applied setting, we have not only the way of explaining the outputs of our neural network, we also have the means of forcing it to do what we want it to do. Not in terms of internally, but we can do a sanity check on the output. And that's more than we could before. Okay, very briefly discussing, we've seen that the neural PID controller is superior or at least equal to the PID controller. That's not really a surprise, because it's what we extended in the first place, and we want to be better if we make the effort, I guess. But at least to me, it was surprising that it is also superior to standard model-based controllers in 7 out of 8 tests. And I think the most important part for this community might be, if we use, in this case, traditional control engineering methods, so methods that are applicable and inherent to the application we use it in, then we can gain further insights about the functioning of our systems. And this might even, in this case it does, that might even provide us with a way of enhancing the training in a way that we only get what we want, namely a stable system or stable PID parameters. Okay, take-home message. Extending systems rather than replacing them can be worthwhile, especially if we want to argue with people who actually have to deal with them in the real world, because they're usually not really happy if you come with a black box and say, this is better. Applying machine learning algorithms provides additional challenges, but it also provides opportunities to learn about our algorithms. That's a point that Patrick would probably make the exact same way. And the last thing is, performance should not only be evaluated based on a number that is related to the error, it should also be evaluated with respect to whatever the application calls for. That's basically it.
How do you create the training data?
Similar to how you do it in standard control engineering, what we do is we take the system, or we take a simulation of the system, we apply an input, like usually you do a, I just forgot the name.
Pulse response?
Yeah, thanks. A Dirac impulse, so like a 1 and then nothing anymore, and then you can, as this impulse traverses through the system, you can get an idea of how the system reacts to whatever impulse. And this is what we did, different impulses, and then we collected data about that.
And you had a differential equation model or something? You had a differential equation to model?
Yeah, exactly. But again, without the noise and without the disturbance. Yeah.
In the discussion you mentioned you compared it to model-based control.
Yeah.
Do you mean MPC, model projective control?
No, I basically mean LQR, which uses the model, and backstepping, which uses the Lyapunov model.
The result that you showed in a fluid system.
Yeah.
So you showed the PID.
Which one? Oh, this one.
This one.
Yeah.
So I'm not sure if it is a scale, but it seems that the KD didn't really change.
It's a scaling thing. It did change to an extent, and actually the KD is what makes it unstable in a stability guaranteed way. For this, I had a lot of discussions on that. It's really difficult to say, because sometimes you want something that is nearly unstable, or that is in fact unstable because it is more aggressive. Like it might be more beneficial if you're down here to exchange stability for an aggressive way of getting back to where you want to be. That is to an extent theoretical though. Like I don't have proof. That's what's the outcome of a lot of discussions with actual control engineers.
And is it the raw data or is it smooth result? Did you have to smooth?
No.
Regarding the input to the neural network,
Mm-hmm.
instead of feeding the current state, wouldn't it be better if you feed a difference vector as in some time step t minus the current? So that gives us, for instance, in the case of pendulum, it gives us the velocity of the
Well, you can do that, yeah. That requires memory outside of the system, and I wanted to specifically only use what would be available in the PID, in the traditional PID setting. Like I wanna extend whatever is there with the least additional amount. That's a choice. You could very easily say, I'm just gonna add states and just add more things, but not necessarily better. We did some experiments where we did that, where we had like a neural network with more inputs that had external dynamics. They performed slightly worse, which might be due to limit amount of experiments, but they did not perform better as far as we could see. I guess that's what I want to say. Yeah.
How important was the recurrent connection in the neural network? Because as I understand it, the error is being fed back in. So
Yeah, that is definitely important. Like we tried simple feed-forward networks. We tried feed-forward networks with an external dynamic, which basically comes down to what he just asked about, like giving past states. Not only had they a significant worse rate of convergence, meaning they did not converge at all to stable solutions, they also just performed pretty crappy. Matt?
So when you're tuning a normal PID controller, you're using the same data that you're using to train your neural network, right? Or are they getting that? Like when the engineer comes in to tune the PID controller,
Yeah.
he uses data similar to what you used?
Yeah.
So did you need much more data to train your neural network, or was it?
Yes, so we did need more data because what the traditional control engineer does is they just use one impulse response and then they assume that the model doesn't change anymore, right? The problem here is, like for example here, the model is usually adjusted to x1 in the upper plot to being x1 being 0, and then you linearize with respect to this area. But if the system is disturbed and you're far away, then your linearity assumption, like your model, doesn't hold anymore. And that's the biggest problem of PID controllers. As long as you are staying very close to what you assume your state is, then you're good. But the moment something happens you don't foresee, the model changes, you have a disturbance that is bigger than what you anticipate, then everything breaks down. Yeah.
Do you have an intuition as to how much you can perturb the systems and still remain stable?
That's a good question. We actually stopped after breaking 2 out of 3. That's an interesting question. I haven't tried that. That's a cool, yeah, thanks. Sorry.
So, like, is it possible, like, you just need to design a new PID controller which will take, which will be stable, like, so this PID system is unstable, but some other PID system will be stable in these situations. And if, like, maybe it's like neural network, if it's like not trained for that type of data, maybe the neural network will become unstable, but PID system is still stable.
Well, the problem is you always need someone to do it, right? And if you have a real world system, like I said, 80% of industrial controllers are PID controllers. If you wanna train so many people sitting there and readjusting PID controllers first of all, it's not feasible because you can't respond as fast as things go wrong. And also, it's just not tractable in terms of cost. Like, there's no way, like, remember Patrick talking about his prosthetic arm? There's like 5 PID controllers just in the prosthetic limb. That basically means while you're using your prosthetic limb, 5 people would need to observe what you're doing and readjust the PID controllers every single day, every hour, every minute. Like, it is theoretically, yes, practically, no way.